after the classes are over, you want to enjoy a little bit the city, there's two places that I really like a lot in terms of something standing like museum-wise. And one is called Instituto Moreira Salles. It's a museum, it's a modern museum. The guy is a famous documentarist. He put a lot of money to make this establishment, where it's mostly temporary exhibits of photographs, video, installation, modern artists. Usually there is a political team attached sometimes, and it's on Avenida Paulista. So it's very, very close to Consolação. So if this is Paulista, and this is our hotel somewhere around here, okay? This is the Trianon Maspi. There is also a good museum. I personally am not fond of it, but it's nice. And here is Consolação, is the Rua Consolação. The Instituto Moreira Salles is somewhere over here, okay? It's very, I like it very much. There is also Museu da Imigração that I personally enjoy a lot. So you can check it out online. I think it's the metro stop is Bracer Moca. It's a safe walk from the metro. And it's a big building, the villa where the immigrants were taken off the boat on the train from Santos to there, and they were screened, and the documents. So it's actually quite interesting. You have documents belonging to 100 years ago, 120, and there's videos, interviews to these people. Okay, so these for what concerns the museums. Then the city center, the historical city center, is an extremely interesting place, but I would recommend actively not to go there, especially not alone, and especially not at nighttime. One very good way to take a walk there and enjoy it is to check the walking tour, São Paulo, or São Paulo walking tour online. And there is always a guide giving a talk either in English or in Portuguese in the morning or in the afternoon, not after sunset, okay? And it's safe, it's a big group, all right? This is for what concerns like more cultural events. And since some of you didn't give me your word, I'm gonna give you some different type of information tomorrow. So Professor Nemmen is currently a professor at USP, Universidade de São Paulo, here in São Paulo, because Universidade de São Paulo is also not in the city of São Paulo, but he's here in São Paulo. He was a graduate student in Porto Alegre, UFRGS, so Universidade Federal do Rio Grande do Sul, where he did his PhD, although he actually spent some time in the United States during his PhD, I think at Penn State. And then he moved for a postdoc at NASA Goddard in Washington, D.C. And then he actually got a professorship at USP, so he's back. And he's gonna tell us about AGNs, and maybe I'm gonna adjust your mic. So thank you, Rodrigo. Probably this way works slightly better. Yes, try
Okay. Can you hear me? Well, this is being recorded, right? Yes. Thank you, Fabio. Thank you for the invitation. Good afternoon, everybody. Boa tarde. Buenos dias. Ni hao, I guess. I don't know. Konnichiwa. Kalimera. Is there any Greek here? No Greek. Okay. Ciao, right?
Yeah.
Okay. And that's it. That's it. So today I would like to give you today and tomorrow a very broad overview about active galactic nuclei and blazars. And I'm 100% sure that you are very excited with everything you are learning. Now you know how to accelerate things, to take particles and put them in non-thermal distributions, I presume. You know how to produce cosmic rays. You know how to produce neutrinos. You know the relevance of neutrinos. What else do they know, Fabio? A lot. They know a lot of things now. I'm sure you are very excited. And now let's see how this, some of this theory applies to the extreme universe. So the content of these lectures is the following. I will give the idea here in the next, well, in the next 3 hours today and tomorrow, right? Today and tomorrow. So I will give a broad overview of the observations and theory of active galactic nuclei, AGNs. And I will put definitely some emphasis on AGNs which produce relativistic jets. They are extremely interesting sources for the newborn multi-messenger astronomy, and also some focus on high energy electromagnetic radiation in particular. The outline of these lectures is the following. So I will begin with historical perspective, then some basic definitions of black hole physics, followed by a tour. We will all go to a zoo, to the zoo of the extreme universe, and we will see the different kinds of creatures, animals we see there, the zoo of AGNs. And, well, so I don't know if you can see, but I put in slightly different colors here. If I had more time, I will tell you a bit more details about the physics of black hole accretion flows and the physics of relativistic jets, but probably there won't be enough time. I will try, but I am already anticipating there won't be enough time to talk about accretion physics and jet physics, just a little bit, but let's see what we can do. And blazars, we'll spend some time talking about blazars, sources of jets, black hole bazookas pointing in our direction, here towards our planet. So I thought it would be interesting before proceeding, to give you some references that you can go and study after the lectures are over, or tonight, tomorrow, on the weekend, if you want. So for the theory of AGNs, well, the theory of AGNs is general relativity. It's a combination of general relativity, electrodynamics. Yes, general relativity, electrodynamics, and, well, radiative processes affecting radiative processes, which is, somehow electrodynamics. So you need to study these things. This is the theory of AGNs. But there is a very nice summary of the theory necessary to understand AGNs in this old review by Roger Blandford. This review was published in these lecture notes that he gave at the SAIFR AGN school 30 years ago, okay, 1990. So, well, the physics didn't really change, okay? What is improving following Moore's law are computational resources. We are having insights, but general relativity didn't change, and electrodynamics didn't change in the last 30 years, okay? And Blandford gives a very nice review, a very nice summary of the physics of AGNs in this this lecture notes, physical processes in active galactic nuclei. The second work is a standard reference for compact objects. Is the book called Black Holes, White Dwarfs, and Neutron Stars. It's a classic textbook in relativistic astrophysics. It covers a bit of the physics of black holes, physics of accretion disks. It's a very nice book by Shapiro and Tilkolsky. And so if you have a look at these two first references, you will definitely get a good feeling of the theory. And if you want to get a bit more details, I suggest you have a look at this review paper by two theorists, Chris Fragile and Marek Abramovich, Foundations of Black Hole Accretion Disk Theory. And this is a review which has about, I think, 20 pages. They use GR, they use the covariant equations to tackle the physics of accretion disks. And the second review is if you want to have a good idea of the physics of jets. It's a book The Formation and Disruption of Black Hole Jets. One of the editors is Kontopoulos. And in particular, I suggest chapters 3, 6, and 7. They talk about launching of jets, the physics of propagation of jets. This is a really nice book, has some of the leading figures in the field talking about these topics. Fabio, how do I have like 1 hour?
You have 1 hour and 1 hour and 15 for the class and 15 minutes for the
Okay.
This thing is going to produce an annoying sound when it's your
Oh, really? Great. Okay, I was going to put a timer myself here. Cool. Awesome. Right. So these are some suggestions of references for theory. And if you want some references for the observations, observational overview, well, at least from the electromagnetic point of view, okay, of AGNs. But also a bit of cosmic rays. I'm not so sure about neutrinos in this case. It's basically a new field, observing the neutrinos from blazars, basically. But there is this book by Volker Beckmann and Chris Schrader, Active Galactic Nuclei. It's a very nice book. We'll give you an updated understanding of the observations of AGNs. And then I also suggest these review papers. The first one is low energies. It will teach you about unification of AGNs. Relativistic jets, a very broad review by Roger Blandford again. And then the review by Madeshki and Sikora for gamma ray observations of AGNs, mostly blazars. So let's begin here with the first question that we need to address. What is an AGN? Okay. So let me have an idea here. If I asked you, if we did now an interview outside this room, okay, and I call each of you, and we'll give you some financial reward, let's say, maybe, I don't know, or some candy, I don't know. How many of you would know how to define an AGN? Could explain to somebody, it could explain to a graduate student what is an AGN. Can you, well, can you raise your hands who would know how to define an AGN? I think we are suffering in this audience. We are suffering in this audience for something that psychologists, they have a name for this, pluralistic ignorance, where you think everybody knows, and you are the only node that doesn't know a topic, okay, when in fact nobody knows very well, but you are too shy to admit. You know, the psychologists, they know very well this kind of dynamics, you know. We can talk more about this after the lecture, okay? Don't worry, I'm sure some of you, at least 2 of you, know what an AGN and would know how to define an AGN. So my working hypothesis here is that I will assume that you know very little or you never heard about an AGN. Well, you heard, but you don't really know how to explain to a fellow grad student what an AGN is, okay? This will be my hypothesis here for these lectures. Given the lack of reply. But I was shy as well when I was a graduate student. I started grad school very shy, and I ended like this, dancing in public. No, I'm kidding. It was not so. That did not escalated so quickly. Okay. Okay. What is an AGN? Okay. So we have 3 words here: active galactic nuclei, abbreviation AGN. Let's begin with the galactic nuclei part, okay? So galactic nuclei are the very central regions of galaxies. When I am talking about galactic nuclei, I have in my mind a spherical cowl region, the central region of the galaxy, with a radius smaller than about 10 parsecs, okay? More or less 10 parsecs. 1 parsec is about 3 light years. If you ask me to tell you how much a parsec is in meters, I will not know what to tell you. Probably 10 to the 11 meters. To the 18, see? Wow. Okay. 10 to the 18, okay. See, because my mind is tuned to work in parsecs, okay, so I don't care about meters anymore.
Tell them how to convert. Parsec is 3 light years. That's easy to remember.
Yeah, that's easy to remember, okay.
Easy to do 10 to the 10 by 10 to the 7 in centimeters per second.
Thank you.
Right?
We will have our eternal gratitude to you, Professor. Thank you. Okay, 10 to the 18 meters, 1 parsec. Great. Centimeter. Okay. Anyway, it's a huge distance for human scales. So this is what I just told you is what I have in mind when I think about what is a galactic nuclei. Okay, the very central core regions of a galaxy, and galaxies, as you know, are cosmic islands. Okay. So we covered the words number 2 and number 3 here, and now let's cover the word number 1, active. Okay. What does an astronomer mean when they say that the galactic nuclei is active? And then I have it will be a rhetorical question given the lack of participation. But think in your minds and run a simulation in your minds. Is the Milky Way an active galaxy? The cosmic island that we inhabit, is it an active galaxy? Well, we are still alive here, so it's not an active galaxy. Okay, so what is active? What does activate the nucleus of a galaxy? Okay. So what activates the nucleus of a galaxy is the presence of a first of all, you need a supermassive black hole there sitting near the center of mass of the galaxy. That's not a problem. The universe somehow manages to put one supermassive black hole or more than one supermassive black hole at the centers of evolved galaxies. This is a topic of a lot of study, formation of the seeds of supermassive black holes. But okay, so most galaxies, evolved galaxies, they have supermassive black holes at their centers. So what activates is the fact that the galaxy is somehow providing vast amounts of gas particles to the black hole, providing the space-time of the black hole with huge amounts of test particles, okay? And it turns out that black holes have a lot of free energy, okay? And so nature manages to use these test particles to extract the free energy from the space-time of the central supermassive black hole, okay? This is what activates a galaxy. So here is what we have in mind. So this is a cartoon version. This is not a numerical simulation of a supermassive black hole. You have here trillions of particles, ionized particles, swirling in the accretion disk around a supermassive black hole. These are the relevant ingredients of the central engine of AGNs. So, of course, the event horizon. Inside the event horizon, there is this mysterious point, the central singularity, which has all the mass of the black hole concentrated in the central singularity, the realm of quantum gravity. We do not have equations to treat the central singularity. What else? So here, as I mentioned, the accretion disk. There is an important concept which this cartoon gets right as long as if this black hole is maximally spinning, then the cartoon is correct. The innermost stable circular orbit, if this was a Schwarzschild black hole, the depiction of the innermost stable orbit will be wrong. And the photon sphere, which I will also describe very soon in the lectures. Okay, so these are the important ingredients, as well as the relativistic jet, which produces high energy radiation, high energy particles that we love to observe here and spend hundreds of millions of dollars building space missions and ground-based telescopes to observe these particles. So what is the physics necessary to understand, to properly model and describe these objects? Okay. So first of all, general relativity, as I mentioned. In particular, when you are dealing with only one black hole, you will use the Kerr spacetime, the Kerr metric, to model the dynamics of these swirling particles in the static Kerr spacetime. If you have more than one black hole, then you need to do, well, perhaps numerical relativity and vary the metric It will not be the Kerr metric anymore before they merge. And in order to model properly the physics of the plasma and the jet, you need to combine the conservation equations of fluid, of charged fluids, magnetohydrodynamics, MHD, and with general relativity. So the name we give to the resulting set of equations, the covariant version of the conservation equations for a charged fluid, we call it general relativistic MHD, GR-MHD. There is a catch, however. I don't know if Blasi is not here. The two Pasquales are not here in this lecture room right now. Okay. Pasquale squared. You got Pasquale squared in the school. There are at least two Rodrigos in this lecture room, by the way. How many Rodrigos are here? More or less you? No, you are a Rodrigo. Just two Rodrigos here, okay. Right, so because in many cases, in many of the systems of interest, the plasma density is very low, you get into the so-called collisionless regime of plasma physics, and then the MHD approximation is not necessarily a good approximation anymore. You need to do kinetic theory, which you have been solving Vlasov's equation, I heard, right? Right? Okay, so you're dealing with some kinetic theory here. So it turns out that for instance, the black hole at the center of the M87 galaxy, which was imaged 3 months ago, more or less, 4 months ago, you actually need to do kinetic theory to properly describe the flow around the black hole. And it turns out that we do not really have a good general relativistic kinetic theory, which I will call GRK, but there is basically no acceptable code that does general relativistic kinetic theory. Okay, so nobody felt the need to create an acronym GRK, because there are not a lot of people working on this. Right, so the nature, it is really central, literally central to the concept of AGNs that you have accreting black holes. And the source of the huge amounts of energy we observe with our telescopes is the electromagnetic energy, for instance. The source of this energy has a gravitational nature. Okay? Everything is coming from gravitational potential energy of the black hole. And as I mentioned to you, somehow nature is using particles and fields to extract this free energy from the space-time and bring some of it here to our planet Earth. Okay, so now we have a very qualitative idea. What is an AGN? We know that black holes are very important. We know that if you want to understand physically the observations, you need to have some ideas of general relativity. So now let's talk about the challenges, okay? What are the challenges behind observing these systems? What are the big challenges? There are several challenges, but I will point specifically three challenges if you want to observe these systems and try to use your equations to model the observations. The first challenge is I have a story to tell you about the first challenge. Have you heard of the tale of the blind man? There were a couple of blind men or blind women or blind robots, and there was an elephant. Here, there was an elephant. Okay, so I think this is a Chinese tale. I don't remember if this is a Chinese. I think it is Chinese tale. And the blind men were asked by the king to go there without seeing, and then touch this creature, this strange creature, and tell the king, touch one part of the elephant, and go back to the king or the emperor, and tell the emperor what they saw or what they saw with their other senses, okay? And it turns out that if they only have access to one part of the elephant, they will get very different pictures, very partial pictures of what they are feeling, okay? And so as the tale goes, one of the scientists, one of the blind scientists touched this part of the elephant. Oh, it's a spear. Okay. This one, I don't know what he or she is touching there, but he's saying it's a snake. Okay, strange. It's a tree. Okay, it's a tree here. Okay, it looks like a tree. No, it's a blind person. It's a fan. It's a wall. It's a rope. Okay, I hope he doesn't stay there for too long. the person with the rope. And it turns out that this is a great analogy to understand a great analogy to understand the first challenge behind characterizing AGNs in astronomy. Okay. The thing is that AGNs, they are a multifaceted phenomenon in the sense that they are our cosmic elephant. Depending on how you observe an AGN, you will see very different things. Concretely, depending on what energy band you are using in the electromagnetic spectrum, you will see very different things, okay? And because science evolved in this chaotic, nonlinear way, astronomy was not born with access to all wavelengths, okay? So we were seeing particular parts of the picture, and so this did not help putting together a concise picture of AGNs. It took us a long time to have a narrative, a scientific narrative for the origin of AGNs. So this is basically what happened in the AGN field, okay? Radio jet, compact radio emission, broad lines. Oh, not broad lines. Hard X-rays, dusty torus. So this is the cosmic version of the blind elephant tail. The second challenge here is the following. The second challenge started many decades ago when astronomers were monitoring the variation of AGNs. They started monitoring the time series of flux variations of quasars. We call quasar light curves. And the interesting thing here is that they were seeing that there was a coherent variability in the time series with variability time scales smaller than 1 week. Okay, they would see a quasar bursting in 1 week and then fading, or in less than a week. Okay, and I realized that I made a little error here. It should be week there. So variability time scales of less than a week. And when the astronomers went to talk with the theorists, okay, I know I have the time series of variation of quasars. What is powering these quasars? They didn't know what was powering. They didn't know it was supermassive black holes powering quasars. But they had this very interesting time series. They went to the theorists, and the theorists, told the observers that, okay, if you have something varying coherently with time scales less than 1 week, let's say, this implies that the size of the system must satisfy the relationship. There is an upper limit to the size of the system, which is less than the speed of light times the variability time scale. So here, the size is less than 1 light week, okay? Which is the light crossing radius associated with the variability time scale. Why is that? Why is that? So it turns out that it's quite difficult to build any sort of a plausible model of a luminous astrophysical object that varies strongly on a time scale smaller than the light crossing radius. Okay, it's extremely difficult to try to build a model to explain such kinds of coherent variabilities with sizes that are bigger than this. Okay. And the reason is that the separate parts of the object, if they are separated by sizes bigger than this size scale here, they would not be causally connected on that time scale of 1 week, okay? So this gives you a very nice idea that something is powering quasars and it's very compact, okay? So if we translate this to more familiar units, at least to astronomers, This implies that an upper limit to the size of a quasar, the thing powering a quasar, is less than 0.01 parsec, okay, and the parsec units that astronomers love. So a few hundreds of a parsec might look large by our human standards, okay, but this is extremely tiny compared to galactic scales, okay. This is extremely, embarrassingly small, okay, for galactic scales. It's a millionth of a size of a galaxy, this length scale, which is about 1,000 astronomical units. Okay, so one astronomical unit is the distance, the average distance between the sun and our planet. So this is a challenge. This is a big challenge. Why is this a challenge? Because this taught the astronomers that if you compare the size of the sphere of influence of the black hole, which I will give here a rough figure, 10 to the minus 4 parsecs, okay? And you compare that to the typical size of emitting, the observed size of galaxies, not taking into account the dark matter halos, there is a huge, black holes are extremely small compared to the host galaxy. How small? Well, you can do the calculation here. If you do the ratio between the galaxy size and the event horizon size, this ratio is 1 billion, which is coincidentally very similar to the ratio between the classical radius of an atom and its nucleus, okay? This is very similar ratio between the size of a galaxy, the optical size of a galaxy, and the event horizon radius. And also there is another analogy here just for you to have an idea of the asymmetry of scales that we are talking about. If this galaxy was planet Earth, the black hole would be a grapefruit here in this room. Okay, does anybody have a grapefruit here? No, I don't think so. So this leads us to the second challenge in observing AGN. Supermassive black holes are they appear very small in the sky, and therefore they are very hard to observe and characterize. To image, we had to wait 100 years after Einstein published the field equations to image one event horizon. That's how hard, that's how small they are on the sky. The third challenge is a challenge specific, particularly if you are an astronomer and you are trying to characterize the islands in which the supermassive black holes inhabit. So this is one concrete being, concretely speaking, this is a set of 6 images taken with the Hubble Space Telescope more than 20 years ago, actually. This is a very beautiful paper. Was a landmark paper for the studies of quasars. What you are seeing here, for instance, here, you are seeing the image of the host galaxy, but the problem is the image of the host galaxy is being outshined by this huge flashlight located at the center of the galaxy, which is the light emitted by the gas falling onto the accretion disk. And the same thing is happening in all these quasars. And this leads us to the third challenge. So AGNs, they easily outshine their host galaxies, and so it's very hard to observe what is around a bright AGN, okay? They are very bright. This is a big challenge as well. And because we need observations to motivate our theories, we are having trouble getting the observations in many cases. Okay, so we will have trouble building theories. This was a huge historical challenge to have a narrative for accreting supermassive black holes. Right, so we now know the challenges, and now that we know the challenges, let's change a little bit gears now. I will do this in this lecture and also in the next lecture. I will do intermissions with things that I think might be interesting to you. And I think that every graduate student and undergraduate student in physics and astrophysics should read this paper by Steven Weinberg. It was this article was published. I stole this slide from Kentaro Nagamine. I think Kentaro was lecturing in a school we organized. There is a gentleman sitting there in the back. He organized a very nice school on the dark ages of the universe, the reionization of the universe. And Kentaro was lecturing. And I shamelessly stole this slide from Kentaro. So I think you should all read this paper, this article by Steven Weinberg, Physics Nobel Prize from 1979. Weinberg gives 4 advices to young science students, young researchers. Lesson number 1, learn to swim as you try not to drown. In other words, don't wait to study everything in the field you are working on before you start getting your hands dirty, okay? If you want to learn everything, you will not do anything new, okay? This is especially true in astronomy. Every day there is a new observation. If you wait to study everything, you will not do anything new in science. Number 2, aim for the rough water. In other words, try to find where the action is happening in your field. Try to avoid things which are established. You will not get anything new there. Don't go for the boring things, go for the state of the art. Number 3, forgive yourself for wasting time. And number 4, learn the history of science, at least the history of science in your field, because that will give you a perspective of what is happening and what will come. Okay, learning history is always good. The history of particularly the history of science, the history of mankind, or humankind. And motivated by point number 4 that Weinberg is doing here, I would like to give you now a historical perspective on AGNs. I will summarize here more than 200 years of history of studies of supermassive black holes. Starting with the first landmark in this historical perspective of AGNs happened in the 18th century, 1783. Reverend John Mitchell used Newtonian mechanics, and he proposed the existence of mythical dark stars, which would have a gravity so strong they would slow down light and imprison light. Okay, so this was the one early version of what we now call black holes. Of course, it makes no sense to talk about black holes in Newtonian mechanics. You cannot have a black hole in Newtonian mechanics. Then we have, of course, Einstein publishing the field equation, 1915. And then shortly after he published the equations, there was this German gentleman, Karl Schwarz, working in the Prussian army, finding some free time between calculating ballistic trajectories of cannons. He derived what we now call the Schwarzschild solution of Einstein's field equation, the Schwarzschild metric. This is really amazing. So this was very important. It's the black hole solution, at least the first and the most simple black hole solution. And then we have something very interesting. Astronomy starts giving input to general relativity. Well, the feedback between physics and astronomy took a while once this observation was taken. So in 2 years after Schwarzschild derived the Schwarzschild metric, the astronomer Curtis, he was looking with an optical telescope to the galaxy that we now image the event horizon, M87, and he made a comment. There is a curious straight ray connected to the center of the galaxy, a very curious straight ray. Nowadays, when you see straight rays in some images, you think it's a cosmic ray or something damaging your image. But back then, there was not this concept of. He didn't really know what to say of this curious straight ray in galaxy M87. This is a very important observation because this was the discovery of relativistic jets powered by black holes. Then it took almost 50 years for the discovery of quasars. The Dutch astronomer Martin Schmidt found a very strong optical source at the center of the quasar 3C273. People thought it was a star. It was a crazy star. But then eventually they measured the red shift, and then they found out that this very bright astronomical source is actually located almost 1 billion light years away from our planet. Okay, so what is powering such a bright object? Okay, this was the discovery of quasars and that they are at cosmological distances. And then it took quite a while. Of course, I'm doing a selection. I'm not listing here every single important historical development. Otherwise, I would spend the rest of 1 month talking about the history of the field. Another very important historical event was in the early 90s with the launch of the Hubble Space Telescope, HST. And so Hubble was very important besides giving an exquisite measurement of the Hubble constant. Hubble also found these dark, massive objects at the centers of nearby galaxies. This was extremely important because then Hubble found and firmly established the existence of supermassive black holes at the centers of nearby galaxies. Here I'm listing the papers if you want to have a look, a lot of papers, but this is the two first ones. They are very beautiful papers establishing the existence of a supermassive black hole at the center of M87, and this is a review paper. And then in the late 1990s, there was another breakthrough by the group of the UCLA group of Andrea Ghez and also the group of the German group of Genzel. They were able to pinpoint, to image individual stellar orbits around the center of mass of the Milky Way. And they were able to measure the mass, this dark mass at the center of our galaxy. And they firmly established the existence of the supermassive black hole at the center of our galaxy, which we call Sagittarius A star, with a mass of 4 million solar masses inside the event horizon. And Sagittarius A star remained the strongest the strongest case for a black hole until 3 or 4 years ago with the gravitational waves that established the existence of firmly established the existence of stellar mass black holes. I will try to move a bit quicker now. So as you will see, things start accelerating. The rate of discoveries starts accelerating. In the late 90s, in the early 2000s, there was this very important discovery that we now call M-sigma relation. So M is a property of the central black hole, and sigma is a property characterizing the velocity distribution of stars in the bulge of the galaxy. And so there was this discovery of this correlation. Somehow the host galaxy, measured in terms of the sigma property, is talking to the central black hole. And this was not expected. I will give more details why this was almost completely unexpected by the theorists. So they established that supermassive black holes and host galaxies are tightly connected. This was a major surprise to the theorists. They didn't see it. Almost 95% of the theorists didn't see this result coming. This is the birth of the field we now call AGN feedback, the feedback loop between the central dark mass and the host galaxy. Then in 2000, a few years afterwards, there was this other very important result that supermassive black holes, apparently they are able to substantially disturb the thermodynamics of entire galaxy clusters. This was a huge surprise. Then in 2003, this survey, this astronomical survey called Sloan Digital Sky Survey, discovered more than 100,000 quasars on the sky. Okay, so this was a huge breakthrough. So supermassive black holes, they are not rare. For every galaxy basically has a supermassive black hole. But this was observations, concrete spectral and imaging observations of this more than 100,000 quasars. And now we get to 2015 with the historical Nobel Prize winning direct observation of gravitational waves from the merging of stellar mass black holes. And why should I mention a result related to stellar mass black holes in a lecture about supermassive black holes? And the reason is that this was really important because you cannot really now question that there are no black holes in the universe. Okay? Nobody questioned in 2015 that there were no black holes. A couple of people still talk about gravastars and some other boson stars, some strange objects, but it's just a minority of the community that questioned black holes. Black holes were already a paradigm, a scientific paradigm 4 years ago. But this really firmly established using the sound of space-time, gravitational waves, that black holes do exist. You cannot explain the waveform without the black hole solution. Finally, we now have 2018, the first multi-messenger observation of an AGN, the blazar TXS. I will not pronounce the WhatsApp number of the blazar. And by the way, next week we will have a hands-on tutorial where you will learn how to analyze the gamma ray observations of this blazar, right, Fabio? So Fabio there will teach you how to reproduce unfortunately, you will not be able to publish this again because there were already a couple of science papers with this result. But Fabio will teach you how to reproduce the result in the science papers, okay? Right, Fabio? Okay. But maybe in another blazar you can still analyze and publish a Nature or Science paper. Who knows? Okay, so gravity. Okay, I will skip the result by gravity. I will go directly to now. I am sure that all of you saw the EHT image 5 months ago, which was really a breakthrough in black hole physics and black hole astronomy, where the first image of an event horizon in the history of science, and precisely the first Curtis observed the jet from this object 100 years ago, and 101 years later, we observed the event horizon. This is amazing, the evolution of science. So, what are the lessons from this broad historical perspective on the study of, what are the general lessons we can learn from this broad spectrum of discoveries? The first lesson is that we can write an equation. If you take the dot product of new technologies with engineering advances, okay, you open, that equals new astronomical windows being open for science, okay. On the other hand, if you take the cross product of the new observations produced by these new astronomical windows, you take the cross product with grad students, and you get paradigm change, okay. So we can write these two equations here. The lesson is that every time a new astronomical window is open, the universe turns out to be far stranger than the wildest speculations, okay? So this is one of the lessons we learned from these discoveries. We have a couple of other lessons. The pace of discovery is accelerating. If you pay attention to what's happening in every field of science, in particular AGNs, there is a huge discovery space awaiting for you to participate in the scientific narrative. And in my opinion, we entered a second golden age of black hole physics. With the LIGO-Virgo results, we entered a new golden age. The first golden age, the physicists that specialize in the field theory of GR, they call the epoch of the 60s. They call it the first golden age, 60s to the early 70s. And I think we entered a second golden age of black hole physics, driven by observations, not only analytical calculations and simulations, but mostly observations. Okay, so now that we did this broad historical overview, let's talk about black hole physics. So my idea now over the next 20 minutes or half an hour is to give you the next 2 minutes. We'll give you a very broad overview of black hole physics. And if we want to understand black holes, we need to understand general relativity. I'm not sure how many of you took a course of GR as an undergraduate students or graduate students. I don't think I will ask. Should I ask? Okay, who took GR already? Okay, there is way more participation. Okay, so most of you, good. Okay. So I'm surprised that most of you never heard or don't really know about AGNs. But good, it's really good. It really gives me motivation to continue this lecture. Right, so, well, general relativity primer, the theoretical substrate of black holes. So we begin with the field, Einstein's field equation. Okay, we have all the well-known tensors there, the Ricci curvature, the scalar contracting the tensor on the left side, the metric, and on the right-hand side we have the stress energy tensor with the fundamental constants of gravity. And the equation, this equation really means that on the left side you have the space-time curvature, and if you put the input on the right-hand side feeding the matter-energy distribution of some system, and you solve this equation, the equation will spit out what is the space-time, what is the curvature. This is, you can only solve Einstein's equation analytically for a couple of cases. If you start putting more astrophysically interesting cases like merger of black holes, merger of neutron stars, it gets very complicated to solve Einstein's equation. And once you have the curvature, once you solve for the mass energy distribution, this tensor metric encapsulates the space-time properties. And then you can characterize geometries with the tools of differential geometry, the line element, which tells you the infinitesimal distance between points in space. And finally, you use the geodesic equation to learn about the motions of test particles in this curved space-time. So this is a summary of GR in 1 minute or perhaps 2 minutes. And GR predicts the existence of black holes. So black holes are these remarkable predictions of general relativity. The central difference between a black hole and a normal astronomical object is the presence. So whereas a normal object has a solid surface like this planet, or even a gaseous atmosphere like a star, black holes, they don't have a solid surface. So a black hole has the surface of a black hole, or we can call it a membrane, we call it the event horizon. It's not solid. If you cross a black hole, it will dive inside the event horizon. We will not crash in the event horizon, and it will keep diving inwards until you reach the singularity, and you are crushed by the tidal forces near the singularity, or even before you reach the singularity, okay? So this is the property I just described to you. The existence of an horizon, of an event horizon, is one of the ways that you can test the presence of black holes in astronomy, okay? If you throw a lot of particles in an object with a surface, eventually the kinetic energy of the particles will be converted to some other form of energy when the particles collide in the surface here. If you do the same with a black hole, they will go inside and you will not see this necessarily colliding with anything. They will not collide with anything. Right. So the event horizon is a one-way membrane. Once you are inside the event horizon, you are doomed to meet the singularity in your light cone, okay? You are doomed to meet the singularity in your light cone once you get inside the event horizon. It's causally disconnected from the outer universe, from the solution of the outer space-time outside the event horizon. From the Schwarzschild solution, from the Schwarzschild metric, you derive that the radius of the event horizon is 2 times g times the mass m of the black hole divided by the square of the speed of light. So this is 3 kilometers for a black hole with the mass of the sun. Also, another meaning of the Schwarzschild radius is that the gravitational time dilation goes to infinity near the event horizon. Another important another length scale that will be important here for the course is the gravitational radius. This is very important in relativistic astrophysics. Is the Schwarzschild radius divided by 2. This is a very useful scale when you are talking about black hole astrophysics. Okay. So what happens when black holes interact with their environments? So if nature is feeding black holes with particles, what will happen with the mass of the black hole? It will go up, of course. The mass of the black hole will go up when the black hole accretes particles. And if particles keep falling onto a black hole, they will penetrate the event horizon. And because the mass will increase, they will add up to the mass of the black hole, the Schwarzschild radius will grow as well, because the Schwarzschild radius depends on the mass. And the surface area of the black hole will also increase. So it's interesting, it's important to point out that there is no limit to how big an astrophysical black hole can grow in mass. The smallest mass that we have measured for a black hole candidate in astronomy is about 4 solar masses. And the biggest mass ever measured for a black hole in the center of a galaxy is more than 10 billion solar masses. Okay? So let me tell you, we do not know any law of physics that gives an upper limit to the mass of a black hole. The limit here is the cosmological evolution of galaxies and the structure formation. So this leads us to this understanding, the popular understanding that it's once inside, nothing escapes. So if you take, let's say, a nuclear bomb, put a timer to explode, dump the bomb inside the black hole, it will explode inside the black hole. You will not see anything happening. You will never see the heat and the light and the neutrinos produced in the nuclear explosion. If you take now 2 fat, massive objects, let's say 2 fat, massive stars, and you throw inside a black hole, the black hole, as I taught you, it will grow in mass, okay? You will not see necessarily, well, something will happen with the massive fat stars. If you throw, okay, let's say you take now a black hole, okay? You take an object that never gives you anything back. It only consumes. It only annoys people. It only stresses out people. It only consumes. You take 3 black holes, okay? And you throw into another black hole, okay? It will grow in mass, okay? So something similar to this happens this is one of the main factors driving the mass evolution, actually, of supermassive black holes in the centers of galaxies, collisions between things that do not give you anything back. But even black holes are, well, okay, here in this case, you don't need to throw this person in the black hole. This person will throw himself in the black hole, okay? It will be very easy. You don't need to do anything. But anyway, so black holes have no hairs. So what does this sentence mean? A black hole has no hair. It means that the black hole solutions of Einstein's field equations, they are simple in the sense that you only need 3 parameters to describe the black hole solutions. These parameters are the hairs of the black hole solutions. They are observable classical parameters. You can measure these numbers. The mass, the spin, which is related to the angular momentum of the space-time, and the charge. And one way of translating the spin, the angular momentum, as a dimensionless number is putting the angular momentum with this spin. We call it spin parameter A. The spin parameter goes between -1 to 1. -1 is when the black hole, okay, suppose I am a black hole, okay, I'm a black hole, and this is the sense of rotation of the accretion disk around me. So if we are doing this, if we are rotating counter to each other, I'm sorry, maybe I'm not helping here with my analogy, but this is a retrograde case of accretion, okay, I'm spinning this way, the gas is spinning the other way, then the spin is by convention -1. If we are both spinning in the same way, oh, okay, hello, accretion disk. We are spinning in the same way. This is the prograde case, and by convention is +1, the spin parameter. So there is the famous Nohair theorem, which I like to call in Portuguese, Teorema do Careca. It states that all other information besides these 3 numbers disappears. You do not have access to any other property of the inflow. If you have a very complicated star that collapsed and produced a black hole, you will not know about any other property of the star once it collapsed and produced a black hole besides the mass, the spin, and the charge. However, charge is not thought to be important in astrophysics, okay? If you try to put gravitationally important amounts of charge in a black hole, it will neutralize very quickly. Okay, so it's very hard to try to charge a black hole, and that's why theories for the cosmos and for high energy astrophysics that invoke charged black holes are, a bit hard to accept, let's say. I will skip this. I will just mention that if you have a black hole where A is 0 and Q is 0, it's the Schwarzschild metric. If you have a black hole where M and A are not 0 and K is 0, you have the Kerr spacetime. And if you have a black hole where all of them are not 0, you have this complicated Reisner-Nordstrom spacetime, this Reisner-Nordstrom solution of the Einstein's field equation. I will skip this. Let's see. I should mention that, okay, so I should mention that the Kerr spacetime is very interesting. It's a bit more complicated than the Schwarzschild spacetime. It has less symmetries than the Schwarzschild spacetime, in the sense that you have less Killing vectors. For those that study GR, you have less Killing vectors to play with and simplify the dynamical equations. One very interesting feature of the Kerr spacetime is that the presence of this extra degree of freedom, the presence of rotational energy deforms the spacetime. Okay, so this is one of the reasons why you have less symmetries in the Kerr spacetime, and you have far richer astrophysical consequences if you have a Kerr spacetime in nature, which we think that we have a lot of cases of the realization of the Kerr spacetime. Right, now you know the basics of black hole physics, of course, without solving the Einstein's equation. Now we know we have a good footing on the basics of black hole physics. Now let's talk about astrophysical black holes. The thing that fascinates me when I study AGNs, when I work with AGNs, I hope my students are also fascinated by this, is the fact, okay, so they are actively interacting with their environments, these black holes, okay? So only the mass and the spin are not enough, okay, when you have astrophysical black holes. So the two numbers to characterize an astrophysical black hole, as you now know, the mass and the spin. The units that we usually adopt to describe the mass, we talk about black hole masses in solar masses. This is the standard unit in black hole astrophysics. One solar mass is 10 to the 33 grams. The units of the spin parameter, which I will call from now on the A subscript star. Well, it's dimensionless, okay, so do not worry about units for the spin. Just remember that the spin goes between -1 for retrograde and +1 for prograde. If you cannot go beyond 1, well, nobody knows how to make a black hole rotate faster than spin equal 1. People are trying to do that, okay? If you were able to rotate a black hole above 1, it will get a naked singularity, which is the dream of a lot of theorists. Okay, but nobody knows how to create a naked singularity from an astrophysical black hole. Okay, now we need other numbers. Another number you need to describe an astrophysical black hole is this number here, which is we call it the mass accretion rate. It is the rate, the units of this m dot is mass over time. So this is the rate of infalling of matter into the black hole. We call it mass accretion rate. Accretion is a word coming from, feeding, from accreting, from putting matter into onto something. The usual units of mass accretion rate, m dot, in astrophysics are solar masses per year. This is very common. Also, we like to characterize the mass accretion rate in units of this quantity called Eddington mass accretion rate. I will describe what is the physics, what is the definition of this soon. And our dream, when I put my theorist hat, the dream of theorists working in this field is, given these numbers, given the mass, given the spin, given the mass accretion rate, we would like to predict everything about the system. We would like to be able to completely predict the energy output from the system. And when I talk about energy, I'm talking about the energy flowing out from the accretion disk, but also energy flowing out in kinetic form in outflows and relativistic jets that we call in astrophysics. Let me suffice to say that we do not have a full theory for this. So there is lots of opportunities for theorists working to predict everything about the total energy output of the Kerr space-time based on these 3 input numbers. And we prescribe energy output in astrophysics usually using ergs per second of power, or in terms of the so-called Eddington luminosity, which I will define very soon. Okay, another thing I should mention is that some people, myself included, think that a 4th parameter necessary to describe astrophysical black holes, besides M, A star, and M dot, is the magnetic flux. Okay? It is not very clear to us what is the role of the magnetic flux, but it turns out that when you feed magnetized plasmas to a Kerr space-time, you can have very interesting consequences. So it seems to the theorists that the flux, the magnetic flux accumulated near the event horizon, is an extra important parameter. But to first order, let's only worry about these 3 numbers, okay? Magnetic flux will come tomorrow. Okay, so this is the main problem in black hole astrophysics. We want to predict, as a function of time, the appearance and the behavior and the energy output of AGNs. Once we provide the mass, the spin, and the accretion rate, in practice, this means specifying initial conditions and boundary conditions, putting the space-time, and trying to see if what we get is nature, is the observed universe. Also, people want to do a GRB over time function and a stellar mass black hole time function. Okay, so this is not only AGN, but stellar mass black holes and gamma ray bursts. Also, we want to describe them. This is the dream of theorists working in black hole astrophysics. We also want a function for AGNs, GRBs, and X-ray binaries. Okay, Fabio, how much time do I have?
You have 10 minutes for the class.
10 minutes, okay. 10 minutes, very good, very good, very good. I'm very slow as usual. But I think it's important to get the basic concepts here. Okay, so let's begin talking about important quantities that you need to understand the literature and results of AGNs. Beginning with this quantity called Eddington luminosity, which I just referred to in the previous, 2 slides ago. So what is the Eddington luminosity? Okay, the Eddington luminosity is the following. Suppose you have a central object with a mass m, and this object is radiating away a photon field. Okay? So the central object, it could be a star, it could be the energy flowing from cities on a planet. Okay? It could be an accreting black hole. It can be anything. It doesn't really matter what the central object is. Suppose this object is producing a photon field, a radiation field, and we can describe this photon field with a luminosity. Okay? A luminosity, the power in radiation emanating from the central object. As I mentioned, it can be a central black hole. We can ascribe this concept to an accreting black hole. And imagine that you have a plasma of electrons and protons that are surrounding in a spherically symmetric way the central object with a mass m. Okay? So you have this plasma of electrons and protons which are talking to each other with the Coulomb interaction. And let's suppose a pair of electron-proton at a distance of r from the central object. Okay? So the basic question to understand the concept of Eddington luminosity is, when is the radiation field strong enough to prevent the gravitational infall of this pair of particles? Okay? This is the central question that we have to answer to understand what is the Eddington luminosity. So in order to understand what is the Eddington luminosity, The Eddington luminosity is defined when we have the equality between the radiation force due to the radiation pressure on this pair and the gravitational force that is making it fall towards the central object. So we define the radiation pressure, okay, the radiation force over area where the force is acting, and the radiation pressure is the radiation flux divided by the speed of light. So you write in this very nice way the radiation force acting on an electron, okay? Potentially Thomson scattering, doing Thomson scattering to this electron, or the electron doing Thomson scattering to the photon. And then you write the radiation force acting on one electron in terms of the luminosity of the central system, okay? Sigma t is the Thomson cross-section, okay? The classical area, the area associated to the classical radius of the electron. There is a simple way of understanding this result, okay? So now we characterize the gravitational force, okay? So we put the force, the gravitational force is carrying above both the electron and the proton. We have this approximation. So what we do is we solve this equation by putting this there and this there. Very simple, much more simple than what you have been seeing the last week, okay? From what I heard, a little bird told me that you were having fun with the Vlasov equation. This is very simple, okay? So you solve this, and you want to solve for the resulting L. What is the luminosity at which there is this equality? And the resulting L, the Eddington luminosity, is this very simple expression. The expression has the property of the source of radiation, the mass, and the property of the infalling particle, which feels the gravity, and the property of the particle receiving the radiation pressure in terms of the Thomson cross-section. If you write that in terms of the mass, this is the Eddington luminosity as a function of mass. For one solar mass, for a central object of one solar mass is 10 to the 38 ergs per second, okay? What is the meaning of the Eddington luminosity now? The meaning is the following. If you have an infalling pair, or if you have a plasma of an ionized plasma of electrons and electrons and protons, okay? If the central object is radiating at above the Eddington luminosity, what will happen with this pair? If the luminosity of the central object is above the Eddington luminosity, given the concepts the simple concepts that we just described, what will happen with this pair? It will be like, oh, no, okay. It is there already, okay. So this is what happens, okay. The importance of this concept is that it's giving you an interesting physical scale for the luminosity attached to the gravity of the central object, okay. In the sense that, you know, if the object is shining at above the Eddington luminosity, it will maybe impede further accretion. Okay, so this is the main importance. It's a very useful luminosity unit in black hole astrophysics. And the Eddington luminosity gives you roughly the maximal luminosity that can be powered by accretion. Now we define another concept which is very useful in black hole astrophysics, which is the Eddington accretion rate. So to define the Eddington accretion rate, we have to assume there is, again, a central engine which is shining exactly at the Eddington luminosity. Okay, this is our working hypothesis to derive the concept of the Eddington accretion rate. And what we ask ourselves the question, what if this central engine were converting the infalling mass to radiative energy with an efficiency eta, let's say? It can be 10% of the infalling mass being converted to luminosity, mass to luminosity conversion. So the way we frame this is that we write the Eddington luminosity in terms of some efficiency of conversion of the rest mass associated with some influx of matter. So this is what we define as the Eddington accretion rate. So the Eddington accretion rate is precisely this concept from doing this construction, this abstraction, okay? The Eddington accretion rate is the Eddington luminosity divided by some efficiency of conversion of mass to luminosity. Usually this eta is assumed to be 10%. because quasars, lots of accreting black holes indeed have this efficiency of mass to luminosity of 10%. And writing in practice the Eddington accretion rate for a 10 to the 8 solar masses black hole for a 10% efficiency, it is 3 solar masses per year. If you give 3 suns over a year to a supermassive black hole with 10 to the 8 solar masses, it will shine at the Eddington luminosity. Okay? The accretion process will make the black hole shine at the Eddington luminosity. When I say shine, I'm not talking about Hawking radiation. Okay? Forget about Hawking radiation having any interesting astrophysical consequence that we can measure now. Okay? Maybe it has in the early universe, but astrophysicists don't usually worry about Hawking radiation. Okay, so Eddington accretion rate, I think I'm almost over, right? The Eddington accretion rate is a very useful scale for feeding of black holes in the universe. And I will finish with a final concept here, very simple concept before I move on to questions. There is the final concept that I will talk about here is something that we call Eddington time, or some researchers call it salpeter time. I will call it T-Ed. Okay, Eddington was a very, very good astrophysicist in the early 20th century. Okay, there was a clash between Arthur Eddington and Chandrasekhar, and Chandrasekhar mostly won the clashes that they had about neutron stars and other things and white dwarfs. Okay, so Eddington time is the following. Let's assume there is a black hole accreting at the Eddington rate that I just defined. So we write the accretion rate as the time derivative of the mass of the central object. Okay, so if you keep feeding the central object, its mass will go up. So we assume it's accreting at the Eddington rate, so we make this equal to the Eddington accretion rate, and we solve this differential equation. And we define the Eddington time as this time scale that shows up here on the right-hand side. Okay? This is the Eddington time scale. What is the solution to this differential equation? What is the mass evolution over time from this equation? Well, you know what is the mass over time evolution, right? So if the black hole is accreting at the Eddington rate, its mass will go up exponentially with an e-folding time of the, why am I using a laser here, 10 centimeters from the, sorry. So the e-folding time of the black hole is the Eddington time scale. It means that the mass of the black hole will double every 2 years, more or less, okay? And this is the Eddington time scale for 10 to the 8, for the mass should be here. No. Okay, so this is the Eddington time scale. It's 4 10 to the 7 years for a black hole accreting at the Eddington accretion rate. This means that the mass will double every 10 to the 7 years. This is an important time scale for cosmological understanding of the growth of black holes, okay? And that's it for now. Thank you very much. Any questions?
So I have 2 questions. The first is, what classifies a black hole as supermassive or not supermassive?
Yes, okay. So what classifies, I have a slide for this, but I will describe you. It's the mass, it's only the mass. So supermassive black holes, it was kind of an arbitrary notation, okay? But supermassive black holes, they have masses above roughly 1 million solar masses inside the event horizon, okay? So if you look at a galaxy, and you measure the mass of the central black hole, and it has over 1 million solar masses, we call it supermassive black hole, like the song by Muse, right? There is a song by Muse, right?
Yeah.
Fabio, you're laughing, don't you know? If it were a Ramones song, you will know. Okay. And a stellar mass black hole, usually stellar mass black holes we define as having a mass very close to 1 solar mass, okay? So if the mass of the black hole is very close to 1 solar mass between 3 solar masses and 60 solar masses, we call it a stellar mass black hole. And there is also a putative class of intermediate mass black holes, which should have, they are in between the two extremes, okay? So usually 1,000 solar masses, 10 to the 4 solar masses. So these are really, we like to classify things, and so we put these different tags for them depending on the mass scale. And it turns out that actually these tags are relevant for astrophysics because apparently the growth modes of these black holes are different depending on whether they are stellar mass black holes, supermassive, or intermediate, okay?
Was your question more related on how you form them or just how you define them? Was your question more related on how they happen to exist or how do you define them?
How do you define them?
Okay.
Yeah, well, the question by Fabio is how do you form this supermassive, well, it was not a question, but how do you form supermassive black holes? We don't know. Okay. This is one active area of researcher. Yeah, it's one active area of researchers and one active area of research. Suffice to say, we don't know. There are 3 channels that we think there is some kind of instability that produces something very massive at the early times of the universe. By early times, I mean in the first billion years of the cosmological evolution of the universe. And there is somebody here in this audience which is an expert in the seed masses of the first supermassive black holes of the universe. And this person is there with a very nice shirt with pandas. It's very easy to recognize him. So we can chat about this. It's a very interesting topic. Yeah.
And the second question is, you said that AGNs have a curved space-time. But that means the black hole is just spinning, but have no charge. Can you have charge in the black hole of an AGN with Kerr-Newman space-time?
I forget what is the Kerr-Newman. The Kerr-Newman is the space-time where you have charge and no spin, right? The spin is 0, but the black hole is charged? No,
it's spinning and have charge.
Spinning and have charge. Okay. Well, Kerr-Newman, well, so this is the thing. We know that black holes must spin. Every black hole in the universe must spin at some point in its history because of conservation of angular momentum, okay? Let's think, okay, the origin of small, tiny, cute black holes in our galaxy. Our galaxy has millions of stellar mass black holes, and many of them, they are born from the deaths of massive stars with masses above 10 solar masses or something like that, okay? So the thing is, stars are usually rotating, okay? To different degrees, they have angular momentum, okay? I don't think you will find a star which is completely static, okay? And as the star collapses, what happens with the spin of the star, okay? This is very easy. Like if you dance ballet, I probably suck. I never tried dancing ballet, but all of you saw this example in Physics 1, where there is a ballerina, and then the ballerina is doing this, and then she's just like and spins faster, right? The same thing happens with a collapsing star. It will start spinning faster, and the resulting black hole will be born spinning, okay? So spin certainly is important at some point of the life of black holes. We do not know if supermassive black holes are rapidly spinning or not. That's a different question. Charge, we know it's irrelevant, okay? Because what happens if you take a black hole and you throw a lot of electrons, you take a block of pure electrons and you throw in a black hole and you try to add negative charge, a global negative charge to the space-time. The thing is that it will put a temporary negative charge, but then this negative charge will start pulling positive charges, okay? And that will result in the discharge of the black hole in a very quick time scale, okay? So this is a qualitative argument, of course. The relativity physicists, they already proved, they have arguments, very strong arguments why we do not, black holes will discharge very quickly. They will get neutral very quickly, okay? And don't be, remember this thing called pluralistic ignorance, okay? Sometimes you think that everybody understands what's being discussed and you are afraid of asking a question to embarrass yourself, but this is what is pluralistic ignorance? It's an asymmetry between what you think and reality, okay? But usually people are as lost as you, okay? So if you are the brave first person to ask the first question, more questions will follow, okay?
Hi. And here.
Okay.
At the beginning, you mentioned that accretion disks are collisionless plasmas and should be properly attacked with kinetic theory, but people use MHD codes to perform simulations, and how much wrong could the results be, or
I love it.
How far?
I love it. I love it. Thank you. Thank you for this question. Well, we have, when you talk with plasma astrophysicists, they love to do MHD. All the universe is MHD. The atmosphere of a galaxy cluster, let's use MHD to tackle that. Let's use MHD to tackle black hole accretion disks. In many cases, it's, as I mentioned, you can do a plot of the mean free path versus, you can make some nice plot to characterize the plasmas of these low luminosity AGNs, and they are in the collisionless regime, okay? And quite honestly, they might be, they're probably doing close to okay, I will not call it a zeroth order approximation to the physical truth, first order approximation, but this is not really answering you anything. I will give you some more concrete examples, okay? So for instance, for non-thermal electron heating in these accretion disks in objects like M87, nobody knows how to do it, so you cannot really trust anything about non-thermal that is happening in the community. If you hear somebody talking that everything is MHD, everything in black hole astrophysics is MHD, that's a red flag, okay? Be very careful. A more intellectual, honest is saying, look, you know, we know this is, I will not call it wrong, okay, because I don't want to buy fights with colleagues, but it can be missing a lot from the physical truth, okay? But be suspicious of people that claim that MHD solves everything. It's just it's an approximation, which is, you have a lot of codes that do MHD, okay? And basically 1 or 2 codes that do kinetic, general relativistic kinetic theory. So my advice is be suspicious, okay, if you hear somebody saying that the MHD is the answer to life and the universe, okay? I can give you more concrete answer in a one-to-one talk, okay, to your question. Sorry for being vague at this point.
Hi. My question is, what is the origin of those jets?
Next lecture. Kerr space-time with magnetized plasma and large-scale magnetic field lines. For now. Tomorrow, the more complete answer.
So, hi, it's more like a curiosity. So you mentioned Hawking radiation. Is there any way to measure it directly or indirectly?
No. No. I want to prevent my computer from sleeping here. The full answer is the following. It was not easy to derive the Hawking radiation. It was not easy for even for Stephen Hawking, it was not easy. Maybe it was easy, I don't know, I don't know. But the result is very simple to use. The resulting formula for the temperature, the black body temperature of the near horizon, of the near horizon surface near the black hole. It's a very simple formula of black hole thermodynamics. And you can compute as a function of mass the temperature of the resulting radiation, the thermal radiation that has a very nice black body shape from the close to the event horizon. And if you do this calculation for a supermassive black hole, I get this question in very often, and I never remember the result, but I think the luminosity is about 10 watts, okay? It's something like that. It's like of the order of watts, comparable to the luminosity of one of these lamps here. And that's impossible to detect, okay? If you were God, if you believe in God, God can probably detect. I'm an atheist, okay, let's make it clear. But if you were God, you could probably measure this Hawking radiation. But if you give 1 kilogram of gas in the accretion disk, it will probably shine brighter than this Hawking radiation, okay? If you just give the tiny bit particles, and they have enough density to start having magnetorotational instability, have friction and release heat as radiation, it will shine brighter than the Hawking radiation, okay? That being said, there are some heroic efforts happening in at least one place of the world, in an Israeli lab led, I think it's the Hebrew University, led by Jeff Steinhauer. And Steinhauer is doing some very interesting results that were some very nice calculations by always Bekenstein, Jacob Bekenstein, very famous physicist in relativity, the golden age of GR. And he noticed something very interesting, that you can, depending on how you frame the equations, you can make a system with a fluid without gravity that follows the same equations as a black hole with a gravity, okay? A fluid gravity correspondence. I'm not talking about ADS, something dualities, which fascinate most of the physicists in IFT, this duality. And then the hope of Steinhauer is by playing with the speed of sound in the fluid with a Bose-Einstein condensate, and by playing with the speed of fluid, his hope is to create some kind of analog horizon, okay? It's not an event horizon in gravity. It's an impostor, okay? It's an impostor. It might be fake news in the sense that we do not know if that will really teach us about gravity, okay? But they claim, there was a Nature paper a couple of months ago, and they claim they're seeing the analog of Hawking radiation in these tabletop Bose-Einstein condensates. Again, word of caution, that's not gravity, that's not a black hole, it's a black hole analog, okay? It's the same thing that I'm trying to give an analogy. I'm trying to come up with an analogy here. Is this, I cannot come up with a cool analogy, I'm sorry. It's the same thing as you dating, let's say, you want to date Chris Hemsworth, if you like Chris Hemsworth, the Thor, okay? And you are dating somebody that kind of looks like Chris Hemsworth. You say, oh, this is Chris Hemsworth, you know, I can figure out things about the life of Thor by dating this person, you know. This is the kind of comparison we are doing here. It's not Thor, okay? It's not Thor. The real thing is, you know, or, I don't know, Gisele Bündchen.
I'm not sure I'm following the argument. Anyhow,
is
there any other physics question?
You are not doing the real thing. You are not doing the real thing. That's my analogy.
So that's how we got to that, talking about the Hawking radiation and the creation of an imposter.
What?
Event horizon from which the Hawking radiation might supposedly escape. That's how we got there, right?
To do the analogy?
Yes.
Yeah.
Oh, okay, good.
Okay.
Did it answer your question? Yeah. Oh, good. Great. Is there any other question?
It was a terrible analogy, I'm sorry. I really tried. It was the first thing that
it's
came
okay.
to my mind.
If
It was appropriate
to
talk here. There was another analogy that was not appropriate to talk here.
Hi. Regarding
no, it's being recorded.
Regarding the angular momentum describing the black hole, what does A equals 0 means?
A equals 0, A star equals 0. So A star is the spin of the black hole, as we learned, you know. And A equals 0 means that the angular momentum of the black hole is 0, so the black hole is not spinning. So that's the same as saying that this is the Schwarzschild solution, okay? It's a non-spin. So the space-time is not doing any kind of frame dragging, okay, in the general relativity view of things, okay?
Yeah, but
when
you said like every black hole that have been observed is spinning, so this is pure theoretical?
Oh, okay. So I have to be careful here to phrase things carefully. Physically speaking, we can expect most black holes to be born with some amount of spin. Okay, so they will be born with some spin different than 0, okay? But we do not know what is the long-term evolution of the spin parameter for a given black hole, okay? Especially for supermassive black holes. The reason is that you have a nice or not so nice black hole sitting at the center of a galaxy, and the galaxy is feeding that black hole with gas that is losing angular momentum for different reasons, falling towards the center of the galaxy, and the gas is carrying angular momentum to the space-time, okay? So depending on how the gas arrives at the center of the galaxy, it can either do it retrograde, negative, or positive, okay? But there is another thing that changes. If there is a whole planet, if that star is being accreted by the black hole, I don't know, depending on how that star works, it will change significantly the spin of the black hole. But if there is another black hole crashing in that black hole, it will completely mess up the spin, okay? So that's why I say they are born with non-zero spins, but we do not know the long-term evolution, okay? It's very hard.
So I would say that you can bring any other question in 20 minutes from now because we have discussion. So for Rodrigo and both Pasquales, and we can thank Rodrigo again. Thank you very much.
Thank you.
Coffee break, bell, give me the sign, the form with the signatures back, please. He did not come here? Why do you guys, don't we feed you enough? Why do you eat paper? It must be stuck somewhere because I gave it somewhere over there. So unless it fell into a black hole,